Welcome everyone to Seminar 4. A note again, these meetings will be recorded and posted to YouTube in case you missed it or want to review it. This week we'll be quickly going over the requirements for the next couple of weeks and go through that, but the main thing will be a interesting little introduction to types of sensors and how to interface them that Savash will run through. We've just had a look at the email, so hopefully everyone's got replies to that. And we need to have your market research and costing plan in by Sunday, 31st of May. So please, if you've got any questions on that, raise them at the end. Yep. And again, a reminder to watch the discussion board. Right, well done completing the videos. I hope everyone's got their feedback on those. All been marked. The marks are up in the grade book, so you can check there as well. Just make sure everything's okay. If you didn't have comments enabled on your YouTube site, then Savash would have emailed the comments back through to you. But generally, really well done. Glad to see the effort that went into it, and well done, guys. Okay, so this fortnight, use your teams as a sounding board for developing your prototypes. So we should really be looking at getting the prototypes commenced, or at least have your parts ready to go or your simulation decided upon. The market research and costing report is due, so if you do have any problems with that, please let us know. Same deal applies if you're doing something that is commercially sensitive. Email it directly to the IoT capstone. Okay, and hopefully you've worked out who the most suitable person to advise you on your project is. A reminder on the market research and costing plan, just the breakdown of marks. It's 15% of the overall grade, so it is important, and it will form a significant part of your final report once you've fine-tuned it and got all the, or any bugs ironed out of it. It's going to be 25% on the industry analysis. Now, again, remember that you can do your Canvanizer, look at the strengths and weaknesses in there, the SWOT as well, who you're competing against, who's already in the market, what the industry requires, what you're doing differently. So that will build your industry analysis. Competitor analysis, again, is, go back, please. Oh, sure. Yeah, competitor analysis is 10%, products and services 30%, pricing is 10%, but again, critically important, and the SWOT analysis is 25%, and that can be created again from your Canvanizer document that you've hopefully continued working on. Okay, now, there's something else I was going to say on that, but I'll think of it and I'll come back to it. All right, a big heads up, weeks 9 to 12, are very different to past MOOCs. This is all your effort. It is a capstone project, so we're looking at you doing most of the work with just the advice from us when and where you need it. There is very little content on edX. That is intentional because you should be working on your prototype and then finally writing your final report up. Focus on the discussions within the team areas. Contact us by email if you have an issue or would just like to chat about something, and ask questions of the advisor. This is really what the MOOC is about. It's getting access to expertise that may not be in your own area. So that could be us on the faculty, or it could be your teammates. All right, and that's really what we're trying to deliver in this this final MOOC. It's to show independent ability to research and design a product. That's whether it's physical design or business design, doesn't really matter. So it's up to you to take advantage of that. You'll only get out of this what you put into it. However, each of the sessions we're running over the next 3 or 4 weeks, will have a topic that is the specialist area of each one of the advisors. So this week we're having Savash talk about his work with different types of sensors, how they're interfaced, how to use them. Next week we're talking about pre-production, or how to think about heading towards production with PCB design, designing prototype casings, the first stage in what we would generally term manufacturing prototypes. So something that looks and feels like the real thing, but may not actually be fully functional. Following that, David McMeekin will give us a talk on spatial sciences, GIS, and how that fits in with the IoT. And finally, Val will be giving us or discussing with us how to use and how to access big data. Right. Weeks 12 to 14 are not part of the course officially, but we need those 2 weeks to finalise the marking, get your grades in, make sure everyone's happy with what they've done, and also gives us a chance to help with any further developments, which hopefully we will get. We've had a few that have carried on, not too many local, but in Canada. Where was our heads up one again? Was that Lebanon or?
I think Lebanon, yeah.
Yeah, Lebanon. That we've continued to work with the students on in either commercialisation or PhD research, etc. All right, so that's what the last couple of weeks are about, weeks 12 to 14. So that's all I wanted to cover in the generalities. So I'll now hand over to Savash. I'll keep an eye on the hands up. Feel free to ask questions. And Savash will now take us through sensors.
All right, sure. So, hi everyone. I'm going to give you a very quick overview of sensors, and I won't go that deep into their technical specifications of sensors. So I wanted you to have a general understanding of sensors if you don't have that background, and we'll do that through a couple of examples, and hopefully we can finish off with some notes on energy harvesting, because that was something that was brought up and we've added to this kind of seminar for today. So as a general overview, most systems we require a measurement and detection of the following quantity or condition of a physical, chemical, or electrical characteristic. We usually detect them as on and off switches, and there is a signal coming in, and we want to sense that signal. Now, the basic idea with most sensors is you are calculating a change in voltage, current, resistance, Hall effect, charge, or any other electrical characteristic. And then that electrical characteristic gets translated to a change in environment, change in temperature, change in pressure. And depending on what electrical characteristic you're monitoring, we can either have active sensors or passive sensors. So with active sensors, they generate a signal, normally a current or voltage, in response to that environment stimulation. So what you would be, if you hear the term raw data from a sensor, it's usually a raw voltage data or a raw current data, and it's a change in that electrical component. So you're not directly reading the temperature. And then based on the data sheet and based on what type of sensor it is, that component and that voltage change and current change gets translated to temperature, pressure, and so on. So the examples of these active sensors, we have thermocouples, piezoelectronics, and accelerometer. The magnitude of the generated signal is usually quite small, so amplification is something that we might need in terms of active sensors, and we'll talk about that a bit more later on. So we also have passive sensors. Now the difference is they look into passive quantities such as resistance, capacitance, and inductance. Now, so instead of looking at changes in those, in voltage and current, we're looking at changes in resistance, capacitance, and inductance. And again, at the raw numbers level, it really doesn't matter which change they're giving us. At the end of the day, it usually boils down, when you want to work with a sensor, it usually points down to the fact that you want to see what's the raw value that you're reading from it, and then how can you convert that to an actual environmental change or an environmental like temperature, pressure, and so on. So the examples of these are thermoresistors, thermistor, capacitive humidity, and similar stuff. So these sensors require power sources to generate their information, and often the actual reading or processing is by means of voltage. Now, because we had the discussion about the sensors, I just want to show you some of the more popular sensors that can be used within embedded systems and within these IoT sort of environments. Just to give you an idea, if you have a sensor, how would you typically approach it in terms of just getting data from it? I just want to show you how easy it is. And I'll also show you when you have a new sensor, how I would personally approach finding libraries for it. Sometimes it's just as simple as just looking for a library and the name of the sensor and just Googling it. But I'll show you how you can kind of make that a bit more concise and a bit more targeted so you can find the correct resources. So the picture you're seeing here, this is a pressure sensor. And basically what you do is if you put pressure on that pressure pad, and it's also called an FSR, the resistance of it will change. Now, the way this one is read, as you can see, it's a very simple example code from it. We're basically we have our main setup. We read we basically read the pin that's connected to one of those headers, and the other header goes to the ground. Another example, a very interesting one, is the TMP36. This is a very popular temperature sensor. It's very tiny. Now, you see this equation here? This is what I was talking about. When you're reading the raw value that you're reading, it's going to get converted to an actual environmental change or environmental quantity. And this is what we have here. So if we have another look at the setup of it, it's very simple. You have your ground pin, you have your voltage pin, and a signal pin. That signal pin gets connected to one of the inputs and outputs, so we call them GPIO, general purpose input outputs, on an Arduino or any other microcontroller. And we pretty much read that pin. So if I see, I have the code for it. Basically, with this code, not all of the comments, it's basically in our setup. We're just reading the analog pin that's connected to that signal pin. We're passing it along to that equation that we have to give us the temperature, and then we're printing that temperature on the serial monitor. So again, it usually boils down to you reading something and then converting it to an actual value. And just to show you, because with that specific sensor, we also have a different equation for showing it converting temperature from centigrade to Fahrenheit. So we have that as well. Another very useful little sensor that Ian and I have been using a lot in lots of our projects are IMUs. What they are, they're basically an accelerometer, magnetometer, and gyroscope embedded on the same tiny chip. And they have many uses. We use them in navigation, we use them in aerial stabilization of drones. And what I personally use them for, I use them for the assistive technology research that we have here at Keratin. And I'll talk more specifically about those projects later on, so you can get an example of an active research that's been done on these sensors. So basically, they're a cheap way of getting the measurement of motion and movement. And using these sensors, we can get pitch, roll, and yaw. So this is roll. Pitch is going, if I'm not mistaken, depending on sensor, this can change. So the different directions of the movement. And of course, it's not going to be as accurate as, say, a multi-million-dollar motion camera and motion capture system. But for specific purposes, especially if you're looking at joint movement, they can give an accurate enough results, but much, much cheaper. So these sensors, it can be like, the sensor themselves are probably like $10, like even cheaper than that. And then you add the cost of a microcontroller that's reading off it, and a battery, and a transmitter device. It wouldn't get the raw cost of the device itself wouldn't get more than say like $100, $150. So basically, you'll have the accelerometer in there, and it measures linear acceleration in 3 dimensions. And they're also regarded as gravity sensors, as the reading are equivalent to the gravitational measurements when the sensor is static or under low speed movements. And this is an example of how you can get that, can calculate that acceleration from the data you're reading off the accelerometer part of the IMU. And of course, I have more technical details from that and how we can get how you can measure acceleration in each axis, but I won't go that deep into it because that's to be too technical. But if you were interested in using IMUs, reach us on the email and I'll give you more information. And of course, we have the gyroscope as well, and that helps us maintain and measure orientation. It's based on the theory of conservation of angular momentum, and it involves spinning a rotor in one of the axes. So, again, you have that. You can see the equation for it to measure angular velocity using this the data we're getting from the gyroscope. Now, another important topic when we are talking about sensors is the concept of signal conditioning, which means we want to manipulate the analog signals that are coming in out of our sensors because of the characteristics. So we want to the main ones that are important are linearization, amplification, and filtering. Here's an example of linearization. If the sensor is non-linear, but we are interested in looking at the linearized version of that. That's the type of signal condition we can apply. We have amplification. If we wanted to increase the amplitude of a signal to be able to read it more clearly. And of course, we have filtering, which is very important, especially in terms of IMUs, where they're prone to drifts and noise from the environment. So for us to we usually have to filter that data with some sort of a low-pass signal, a low-pass filter, or popular filters that are used for IMUs are Kalman filters and complementary filters, and sometimes a mixture of these two. And again, on IMUs, they do come with accelerometer, magnometer, and gyroscope, but usually magnometer isn't used unless it's a very extreme case, because they're very prone to electromagnetic interference in the environment. So we can usually get the work done by just using the accelerometer and gyroscope and getting our orientation that way.
Yeah, they're terrible if you've got any metal in the environment. So if you've got lots of filing cabinets inside a building, the magnometer tends to be next to useless.
So an example of a couple of projects we have with IMUs here at Keratin. This is one thing that actually my wife's working on with Ian and David. She's working on a remote training system for visually impaired people. So, and the idea is she's tracking the movement of a white cane, and we can do them with IMUs. And you can see this is the transmitter device that she uses. This is an older prototype. There's an Arduino Pro Mini. We have the IMU sensor and a Bluetooth transceiver. Excuse me. So, and a Bluetooth transceiver. And this is the bit that gets connected to the white cane. And then there is also, so she had two of these sensors, and this is from an older prototype. I think this one is Remy's thesis, because she's following up on one of our other researchers. So basically, we had the sensors connected on a leg, and one of the legs and the white cane itself. And we're not connecting it to both legs because you can get, if you find a correlation between the white cane and one of the legs, you can determine where the next leg would have been. So you don't have to capture that. So that would reduce standard data quite a bit. And then on the other hand, she had a receiver where she was getting that information and reading of it. Another one that I'm working on as a part of my own PhD research. So the same idea, IMUs connected to a microcontroller, and this one is an RF transceiver. This time I'm connecting these sensors on the hand, so on the back of the hand and slightly above the wrist. This is for specifically looking at the joint at the wrist movement. And again, same idea. We use that IMU data to get that information. And This is the transceiver that I use. And then on the other hand, an example of a prototype that Ian's going to talk a lot about next week. But as you can see, it's literally something that we sticky taped to a casing. And as an initial prototype, because we usually want to, as a proof of concept, we want to build something quickly, make sure it works, make sure it gives us the proof of our concept, and then we can move on to making these circuits smaller, building our own PCBs, looking at a more cleaner casing for it, and so on. All right, so I also wanted to give an example of how reading the data would typically look like. So this is from my from the sensor I showed you, the cerebral palsy one. So as you can see, this is just simply a serial monitor reader. It's reading off the serial port of the receiver, and it's reading the accelerometer and gyroscope data. And then later on, I'll get that. I'll pass it to MATLAB, process the data, and get a signal similar to this. So as an example, you can see this is showing the maximum range of movement in a very simple stop sign motion. And because cerebral palsy is something that can affect the range of motion, you can see the difference between the peak of diagrams, one for the normal one, one for the abnormal cerebral palsy one on the left and right. So we can see the comparison there. And another interesting test I was doing during my research that might be relevant here is I was looking at the maximum range of G that I could have for my accelerometer here. So as you can see, because at the end of the beginning of this research, the scale out we had set for our G was set at 2, and we were assuming, okay, that would be enough for the small movements. But when we got the data, it turned out that we were getting cutoffs in the data. So we were wondering, okay, so let's do some tests and just move the hand up and down quickly to see what are the Gs that we would reach. And as you can see, in some cases, we are reaching up to 6 sometimes. So it turned out that we have to kind of change our scale. And as you can see, even though this is just the raw accelerometer data, we are still able to see, you can tell that this was a hand movement. And you can see at the beginning it was a slower hand movement, and in the middle it has suddenly changed into a faster motion, and that was there for us to detect the maximum peak of it. And here you can already see the problems you can have with IMUs in terms of drifting, especially on the z-axis. You can see it's drifted so much down, so it definitely needs to have needs to be filtered, so the data can be actually used without having to worry about the abnormalities that we can see in there. And that sticky tape prototype would reach a stage that we're designing a single PCB for it with all of those transceivers, Bluetooth transceivers, the IMU itself, the battery and the antenna, everything under the same chip. Now, interestingly enough, this has the current pandemic has affected this. We've been kind of waiting on a back order of these because all of the manufacturing in China has stopped. So, but this is the ideal way you want to take your IoT device. You want to, once it comes to implementation of it, you want to first build a prototype, then take that prototype, make a PCB, make a casing for it, and change it to an actual product. So this is the typical manufacturing process to go through. And this is what Ian will talk a lot more about in our next seminar. Ian, do you have any comments so far? Anything you want to add to these?
Well, we do cover a lot of this prototyping, as you've mentioned, next week, but it's all looking good.
All right. Now, another kind of approach to designing IoT devices and embedded systems is going with some of the open hardware, open software kind of devices that are out there. I'll give you a couple of examples of these. So these sensor tags and these small sensor devices, they're usually offered as an open hardware and open software product, and they have a bunch of sensors on them and a microcontroller. Excuse me. They have a bunch of sensors and a bunch of microcontrollers on there. So, for example, this one you can see it has a MPU 9250, which is an IMU. We have an ambient light sensor. We have a digital humidity sensor. We have a temperature sensor. So the idea is, if you wanted to kind of start working on a sensor, you would do something like this. You would develop for it. You would test it, and you would use the sensors that you want. And then, because they offer the hardware as an open source, you can then get their PCB, modify it, and then build your own. So that example I showed you here, this is based on one of these prototypes, because they offered it. I worked there with one of my interns, and we built a smaller version of that didn't use any of the extra sensors that they had, because I was just interested in the IMU part of it. So because that gives you an easier starting point, because you can also pair that with their software. So that gives you a lot of leeway in the future. So this one is this is called Simple Link. It's from the Texas Instrument, and you can see they offer an app for it, and the app is also open source as well. And you can kind of change between the different type of sensors you have, and you can see the movement and the data captured from the sensors in real time. The good thing about this is you can reach a prototype a bit faster compared to starting from scratch and getting an individual sensor connected to an Arduino or a controller. But there are also bad things about it, because then the next step from that, modifying someone else's design, can be challenging. But again, that could be a different approach in building your prototypes and your initial ideas. Another one, so this is the one that was actually that my sensor is built on. This is called NORDIC 52 Tingy. And interesting about the name, I was writing a report on this, and then one of the feedbacks I got from my supervisors was this a placeholder name or a typo? But no, these devices can have funny names. So 52 Tingy, another example of that. This one is from NORDIC. And it has like a bunch of sensors. This one has a speaker, an LED that you can change the light in, a lot more sensors, and the amount of documentation they provide for this device is a bit more detailed. So if you start with something like this, you'll have an easier time with starting and modifying. But
a much higher cost.
Yeah, I think this one is like $40, not that expensive.
Yeah, but again, we cover this next week. It may be $40, but when you're looking at producing tens of thousands of devices, it does become a major issue.
Yeah, definitely. And that's something. Yeah, that's something I would say you would, if you were starting out and you wanted to work with a bunch of sensors, you can get one of these to get used to kind of working with these sensors, rather than having to worry about the physical connection of the sensors, because you know they already work and can look at the type of data you're getting from them. Yeah. And then move on, okay, to something a bit more substantial. And now I'm going to go sit down and design my own thing. All right, and here's the casing for it, and the way it looks like, and the kind of their software interface. Now. How about, I'll cover that afterwards. Another topic I kind of wanted to show you guys is the energy scavenging. So for all of these sensors and actuators and embedded devices that we can design, there are interesting ways of trying to power them by harvesting energy from the environment that they're set up in. So these free and clean energy around us can potentially be converted to electrical energy. And then that would save us time, that would save us our cost, that would save us on having to worry about power, and in the product being more environment friendly. So typical examples of energy harvesting we can be based on solar power, wind power, human motion, and radio frequency. The existing energy harvesters that we can have are photovoltaic or PV cells for solar power, wind turbines for wind power, piezoelectric cantilevers for vibration, and electromagnetic generators for radio frequency energy. And with solar power, of course, they're very popular here in Australia. They're becoming popular in terms of people having a solar battery on their roofs and using that for power. It's popular and it's a mature technology in both research and practice. In practicality, the different sizes of solar panels are offered in the market, from portable solar charger to a solar panel backpack for mobile embedded devices. That there have been a bunch of Kickstarter projects showing up with those. The different factors that may affect the solar power include the shadow effect caused by the cloud and the ambient temperature, which affects your output voltage. We have wind energy, which most obvious example of that are the wind farms, and then when those get converted to actual temperature. Not all of the wind power can be captured because of the conversion techniques that are used to going from wind energy to electric energy. So the efficiency of the wind turbine depends on the actual speed of the wind that's in that environment. We also have kinetic energy, which is where a vibration can be harvested by micro power generators, and they can become a power source for fitness, wristband, wireless sensors, and other portable applications. I'll show you a couple of examples of these projects that are pretty interesting, and how they go from motion to electrical energy. They're low frequency, so they're good for small appliances, but the ones I found, they're not good for a larger capacity of energy if we needed that. And the final type, the radio frequency energy harvesting, which is it's broadcasted from billions of radio transmitters, including mobile phones, portable radios, mobile base stations. This harvesting is supposed to serve as an energy source for low power devices, which makes our products more stable, reliable, and eco-friendly. It supplies power to various kinds of wireless sensing nodes with 24-hour operation. And the problem is only a small amount of energy can be scavenged through this method. So in the rest is dissipated through heat and absorbed by other materials. So that's an interesting area of research. Now, a couple of examples. This one is an electrostatic conversion for vibration of energy harvesting. And you can see it in the picture. Ian, would you mind explaining that for a second so I can?
This picture?
Yeah.
It basically has a suspended mass that allows it to move. So the weight here is actually the part that would vibrate. So you need some mass to vibrate or move with the vibration. And that causes the upper silicon area to pull back and forward on the load, which then is converted into electrical energy through the capacitance and the physical movement. It's fairly straightforward. Just the fact that something moves, you convert that mechanical energy into electrical energy from the static.
Thank you, Ian. I just want to take a sip of my coffee here. Another interesting one. This is a rope-driven wideband piezoelectric vibration energy harvester, which is based on the ropes that are connected to this plank over here. And it's a high-frequency generated beam, and it's driven by an array of low-frequency driving beams here, based on that rope. And it's another example. We had a project, student kind of recently graduated with a similar idea. He had ropes connected to a weight, and then on the other end, they were connected to a basic DC motor. So based on the weight and the rotation of the DC motor, they were able to store battery and store energy that way, which I thought was very interesting. Uh, another interesting project I found online, this piezoelectric shoe by ABEL HAYNES. He basically connected a bunch of piezoelectric sensors as a shoe inlay, and this picture is showing him harvesting a couple of capacitors from a light bulb, and the idea was he was going for a run every morning, and he wanted to use that to charge his phone. So an interesting project he made. So look at his setup with the shoe inlay, and then putting the the power bank there to save, and then charge the phone from there. And this one is showing an example of a hydroelectric generator, which use a flow of water to generate electricity. And see if I have them. Yes. So this is something that Ian and I have been looking at recently, because we're working with one of the insurance companies here to look at water leaks in our households, because apparently one of the biggest costs for insurance companies is if people claim damages for water damage, because then they have to take the family, put them in a different place, pay for their housing, go and replace everything, and this is a big cost for them. They've started to kind of invest in the area of preventing a catastrophic event, and it's interesting that the insurance company is getting into that area. But one of the things we were looking at, because we wanted to use the flow of water that's in the pump to generate the sensors that we are putting there. So this is one we found, and it uses the flow of water to generate that. And the internals of that are basically, I think there's a little turbine in there that works on the basis of the hydroelectric bigger turbines in dams. And there's another one I found, another one on Amazon. This one gives a 12-volt radio power, and it's good for, and it has a bunch of LEDs in there. Have it. I think this one is capable of charging smaller. I can add this as the one. So, and again, an expander of that idea, kind of marketed towards people who would like to go camping, where they can use this to power their iPads and iPhones when they're camping, where they would just put that on a rear flow and then connect the other end to their devices on.
There's also quite a lot being used in rural areas. I just posted a link to some water wheels, and if you've got any flowing water near the farm, these are systems you can just plonk into the river and generate a reasonable amount of power from them. Very useful, as I said, in rural areas, underdeveloped areas, because they're quite cheap to install, and they can power the monitoring system that you're installing on the farm. And they're also nice and green because you're actually not burning anything.
Yeah, and very interesting, especially with this one. I think this came from a Kickstarter project, so that was quite interesting. Now let's start the discussion, answer some questions, and then after I've caught my breath a little bit, I'll show you how it would typically go and get information and start working on a sensor that I get my hands on.
Okay, so do we have any questions initially? That's fine.
All right, so if there are no...
we'll get those IBIS accounts soon, I hope. You're looking at that, Safash?
Yes, I'll look into that after this. We do have access to Curtin, so I'll just have to look up those articles. So I wanted to show you guys this. Let's say I'm looking for information on a sensor. I look into some of the popular manufacturers, like a smartphone, DFROBOT, or something like that. Not to get the device from them, but because with these kind of hobbyist and sometimes industry level product that they offer, they come with hookup guides, Now, with that hookup guide, they'll have information about the sensor pins. Kind of think of it as a more user-friendly data sheet that they offer. They tell you how you can connect it to devices, step-by-step guide in the connection, and of course, also inclusion of sample codes to get started with working with them. So this is where I would typically start working with the sensor. So it's a good idea of looking at these places for initial information. Another place that I usually look at, there is this Australian store, Core Electronics, that has, again, it links to the Spark one, but they have videos there, introduction, sensors, Arduino. Then there's a community around this. So if you want to work with a sensor, it's a good idea to start looking at these types of places and then get your information this way. And especially with any of the online stores you can find, they typically have information embedded there. So you don't have to buy from them. You can just find a product in their store, get the information, and then just go and buy the sensor locally. So that would be an area to look at. There's another thing, I think it was called Tindi, if I'm not mistaken. Tindi is an interesting one. It's like an Etsy for electronic engineers, and people make interesting little electronic PCB level devices, and they sell them. And it's a very good community if you are interested in kind of working on these more low level sensors and actuators and small devices, and look into more technical aspects of IoT. This would be a good community you're going to be involved in. So there are other popular websites like the DFROBOT, Core Electronics, saying that even on AliExpress and Banggood, you can find information to get started. All right. Any questions?
If we haven't got any questions, do you want to talk a little bit about correction of sensors? So we've got the normal IMU problem where they drift off, so you have to find some other way of bringing them back into some form of real signal. But in simpler cases, things like the temperature sensor, they do react to environmental conditions as well. So they're accurate at a certain range of temperatures, but then they start to drift off through the thermal properties of the sensor itself. So normally when you're looking at any kind of sensor, you need to either keep it within its operating environment or have some method of correcting for the flaws within it. And the IMUs are a great example of this, where you need to use one of the other sensors within the IMU to correct the other readings you're getting.
We also we have a question coming in from Gopal. They are asking, could you please share some industrial grade vibration sensors? Can you think of any, Ian?
Sorry, I missed that bit.
Sure. They're looking for industrial grade vibration sensor.
Yes. Industrial grade vibration sensors are not cheap, but if you go to one of the ready suppliers, depending on what country you're in, probably RS Components is a good one because they're global. They will have a selection of sensors. In fact, do you want to bring up the RS Components?
Yep, I'm just opening it up now.
Yeah. Choosing a supplier is a critical decision to make as well. People like RS Components offer you a service that says, if we have something in our catalogue, we have it in stock. So you know that you're going to be able to get it. If they have it in stock, they will get to you same day or next day. So when you're prototyping and you're desperate for getting something quickly, they are a good choice. However, they are very, very, very expensive. You're paying for that service. So if we look at that little RS vibration sensor, the first one in the list, $7.57 in a pack of 5, you would probably find that is a few cents to buy from most other suppliers. However, you won't get the level of service. One of the other things that they also do, if you just slowly scroll down, whoop, not there, everything they sell must be backed up by this data sheet. So they don't just sell you a component without any documentation. They will only sell you products that can be fully documented so you can design from them. So the use of someone like RS Components is really good for your initial prototyping, and then you go and source the product at a reasonable price somewhere else. However, when you get back to the vibration sensors, if you go back one there, Sebash.
Yeah.
You're looking for something, if we look at that second one, that is going to work within the operating temperatures. That's critical. That looks like almost military spec. Okay, so it's got a housing that can handle chemicals in case that is needed. It's completely enclosed. It has the right sort of fittings on it and has a reliability. So somewhere in there will be a mean time between failure. So that is a reliability measure. How long will it operate continuously before it's expected to break down? And that's a critical issue with any industrial type sensor. You quite often will be put into places where it's extremely difficult and therefore very expensive to replace failed components. And of course, because they have all of the information, you will see the data sheet will be available here, and you can select the right product. What you can then do is go to the manufacturer, because they will list who the manufacturer is. There we go, ElectroRead. And approach them directly when you start to look at quantity orders. Does that answer the question?
Yeah, that's right. The IFM is the maker. I also visited that one. So the challenge here is most of the offerings comes with 420 milliamps signal. The boards are, so we need to have a microcontroller before reaching to the edge. Yep. So I need to go with converting those things to 1 to 5 volt signal so that I can interface to the analog input on the board. So I need to put a 250 milliohms in between to convert the 420 milliamps to the 1 to 5 volt. That's what.
So you're using a current loop connection to the
voltage. So, yeah. So the Arduino boards or any boards at the small level won't accept 420 milliamps. So 420 milliamps. So.
Yeah. You should also be able to find current loop to serial converters, which will speed up your development time, and then you can implement your own if it's a cost saving. Just having a quick look.
I found one on RS Components.
RS-232 to current loop serial converter. Yeah. This one is actually for the. It's a straightforward box. Very expensive, but it would save you a lot of time in that conversion. This one's $165. But if you look at your, and this is something you always do in the prototyping, your engineer's wage is probably going to be around $100 an hour. It's going to take him much more than 2 hours to design a build an RS-232 to current loop converter. Okay. So it's actually cheaper to go and buy this very expensive device than to have your engineer develop one initially. When you go to production, it's a different matter.
Okay.
And was it this one here that we're looking at?
I'll pop the link in. This was just the first one that popped.
This one?
Yep, that's the one. Now, that said, there's something else I can mention on prototyping, and that is the simulation of sensors. Particularly in a case like this where there is very limited time and very limited, in many cases, funding available. If you've got something like a vibration sensor that's going to be very expensive, it has to go through this conversion process, consider just using a small, cheap microcontroller that will randomly, but within range, generate the kind of output you would expect from the sensor. So if your vibration sensor is sending out 1,000 samples per second of 16-bit values, you can have a little baby Arduino generating 1,000 16-bit samples every second and talking out the same interface as you would normally use on that sensor. And in that way, you can have something that costs you $4 instead of $500 or $600, producing the range of data that you need for your prototyping, right? So you can do your proof of concept with simulated data.
Sure. Yeah. Probably yes. I cannot afford personally that much money, so I will go with the smaller. Yeah.
Just simulate it. You know what sort of range you're going to expect if you know, a machine is spinning at 50 RPM because it's on a 50 hertz cycle. You would expect the major vibrations to be in that 50 hertz range and harmonics of the 50 hertz. So 50, 100, 150, 200, decreasing down. That is certainly not ideal because the mechanical has a large amount of input into what vibration you get. But at least it'll give you some idea, and you can start working on the intelligence part of the solution, the data processing.
Sure. Yeah.
Also have a look for existing data sets, because a lot of people have already captured data from certain types of machines and other outputs, and you can take their captured data and use that. Oh, there we go. NASA has it. So you could look through this NASA data set for, I'll just pop it in, for a set of data, vibration data that would be somewhat similar to what you're trying to do. Grab that and just have an Arduino outputting that file as the data. Run to failure experiments, run on CFR panel with periodic measurements to capture internal damage growth under tension fatigue. Whatever that may be, because I'm not a mechanical engineer. Okay, we're just about out of time. Has anyone got anything they want to raise? I think we've answered most of the emails that have come in. If not, if you don't hear back today, then give us another yell. That looks like it. Thank you, everyone. It was nice to see you all again. We'll be back tonight for a repeat performance. And, have a good rest of the week.